Hi, I'm Raymond Sheh. Welcome to the Intelligent Robots group at the Department of Computing, Curtin University. In this short video, we'll talk about our preliminary work on the Survey Acuity test method, specifically as applied to aerial vehicles such as drones. We used QR codes in order to perform this test. QR codes of differing sizes represent the ability to see objects at different resolutions. We place these around the environment and record them using a drone such as this under test. We then analyze the video using our software, and from that we can determine what percentage of an area was surveyed by the drone and to what level of acuity. Now, of course, just because we have a particular size of QR code that is detected doesn't necessarily mean that that size of feature is the actual acuity of the drone at that point. This is why we have these calibration targets as well, with the commonly used resolution wedges. We can detect when we are barely able to see the QR code, and at that point measure the actual acuity as a percentage of the minimum feature size. Based on this, we can calculate a correction factor that allows us to determine for a given size of QR code what minimum size object will be visible at that point. Now, of course, being for the Tough Robotics challenge, this test method is designed to evaluate the ability of these drones and other robots to perform under tough conditions. For example, in this environment, we have a tough lighting challenge, with light filtering through the trees and causing these shadows that move across the target. We can use the same test method to compare the performance of the drone in these tough conditions as well as out in the sunlight. We can do the same thing for rain, for wind, and other tough conditions that the drone may face. So of course, this test method tells us what size of object is visible. And this is a very standardized number. It represents parallel lines of a particular size that can be resolved. This measurement is very relevant for comparing different drones or different robots. But in order for responders to understand what this number means, we need to validate it against the actual application requirement. This will be the next step that we will be performing at the Tough Robotics Challenge evaluation event in the middle of the year. During this event, we will perform this test method and alongside them place objects of interest to the responders. We can then correlate the ability to identify a particular object or to find a particular object with the ability to observe features of a particular size. In this way, we can establish a direct link between performance on the test method and performance in the real-world application. Of course, the goal of this work is not limited to drones. In the middle of the year, we intend on testing cyber rescue canines as well as serpentine robots in the context of the ImPACT-Tough Robotics challenge. I'm Raymond Sheh from the Intelligent Robots group at the Department of Computing, Curtin University. Thanks for watching, and I'll see you next time.